We've already seen the polynomial rings with coefficients that are integers or real numbers being used for many of the examples so far in the course. But now we want to look at them more closely, and in particular we want to see how the ring of coefficients of a polynomial affects that polynomial's behavior. And so we're going to look at a more abstract definition of polynomial ring. Before we do that, though, as a little motivation, let's note that the polynomial ring over different rings, with different rings as coefficients, can behave very differently. So, for example, if we consider the polynomial, x to the fourth plus 1 as an element of the polynomials with integer coefficients, then x to the fourth plus 1 is not factorable. This polynomial cannot be written as a product of two polynomials of smaller degree. We're going to look a lot more at factorization in a later lecture. But notice that if we consider the same, a similar looking polynomial over the real numbers with real coefficients, this polynomial is factorable over the ring R adjoin x, because x to the fourth plus 1 is equal to x squared plus the square root of 2x plus 1 divided x squared minus the square root of 2x plus 1, which can be easily checked just by multiplying out the right-hand side here. And so we can see that the properties of a particular polynomial depend on a lot of things, not just what the coefficients are, what the powers are, but where that polynomial lives. Does it live in a polynomial ring with integer coefficients? Does it live in a polynomial ring with real coefficients, or in a polynomial ring with coefficients coming from something else? So to understand this and to understand how the properties of the polynomial of the coefficient ring affect the polynomial ring, we want to understand polynomial rings over any commutative ring. So definition 111 is as follows. Let R be a commutative ring X an indeterminate and I'll come back to this term indeterminate in a second. The ring of polynomials in X over R is the following ring. The elements of the ring are of the form a0 plus a1 times x plus a2 x squared, etc., up to an x to the n, where n is some natural number and the ai's belong to R. So the elements of this ring look like typical polynomials. The difference between these and what we're familiar with is that the coefficients can come from any commutative ring at all that we want to build. And I realized I missed part of the notation here. This is not R, this is R adjoin X. And this is what we, this is how we define it. Now, in order for us to call it a ring, we have to say what the operations are on it. Now, operations in this ring work according to the ordinary rules of adding and multiplying polynomials together. So the operations are defined by the following. if I have one polynomial a0 plus a1x plus dot 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 plus an or am x to the m plus b0 plus b1 x plus dot 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 plus bn x to the n, then adding two polynomials is attained by just adding the coefficients together. So we add the two degree 0 coefficients of the two polynomials to get the degree 0 coefficient of the new polynomial. We add the degree 1 coefficients together to get the degree 1 coefficients of the sum, and so forth. And then we go up to, I'll call it AR plus BR times x to the R, where R is the maximum of m and n. These two polynomials might have different degree. There might be more terms in one of them than the other. And so when we add them up together, we add them all the way up. We just say that we consider ai to be equal to 0 if I is greater than m, and bj is equal to 0 if j is greater than n. So we just add polynomials together by adding together the corresponding coefficients, and we treat any coefficient that doesn't appear as if it were just 0. Now that's adding together polynomials. Multiplying polynomials is a little bit more complicated to describe, but what we're about to write down is really just making precise the normal multiplication of polynomials that we are familiar with from basic algebra. So the product of two polynomials is equal to the polynomial, which I'll describe c0, c1x plus c2x squared plus dot 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 plus cm plus n x to the m plus n, where for all k going from 0 up to m plus n, this coefficient ck is equal to the sum of all the products ai times bj, where I plus j is equal to k. These pieces right here are, as I said, just encoding the normal ordinary multiplication of polynomials. All right, so we've got some additional terminology that we need to use when describing polynomials. Importantly, we need to know when two elements are equal. Depending on what ring you're talking about, a single element could have more than one description. We've seen that a lot with factor rings, for instance. So we need to describe, well, when are two polynomials equal? So we say two polynomials are equal if and only if each corresponding pair of coefficients are equal. So two polynomials are equal if and only if each coefficient between the two is equal. So that means that it's easy to tell the difference between polynomials. You just look at them, and if they look different, then they are different. Now, some terms that should be familiar to us. If we've got some polynomial f, a0 plus a1x up to an x to the n belongs to some polynomial ring. And furthermore, if we assume that an is not equal to 0, then we say that f has degree n. we write that the degree of f is equal to n. Well, we're going to wind up doing arithmetic with degrees of polynomials. Going further here, in this case, the term an x to the n, this term with highest degree, is called the leading term of f. And an is the leading coefficient of f. These are all perfectly standard. One bit of terminology that we have here that we haven't usually run into before. If the leading coefficient of f is a multiplicative identity, of R, we say that f is monic, and if the degree of f is equal to 0, or f itself is equal to 0, we say that f is constant. Finally, the ring R is the coefficient ring of the polynomial ring R adjoint X. Okay, so lot of terms here, a lot of definitions that we're going to be referring back to repeatedly. Most of these terms are ones that we're familiar with, and the operations on polynomials are ones that we're familiar with, which is helpful. Okay, so a few things to note here. Back at the beginning of the definition, I mentioned that x is an indeterminate. In abstract algebra, polynomials are not seen as functions, and so in particular, this symbol x is not seen as a variable. We'll be able to define a function based on a polynomial that involves replacing the symbol x with some ring element. We'll talk about that in just a second. But the symbol x itself is not a variable. It doesn't stand for any sort of ring element. It doesn't stand for anything else. It just is a symbol, and its purpose really is just keeping track of the locations of the coefficients. We could, in fact, define polynomial rings perfectly well without using a symbol like this at all, and just defining polynomials as sequences, finite sequences of ring elements which sit in particular slots. A0 sits in the 0th slot, A1 sits in the first slot, A2 in the A1 in the degree 1 slot, A2 in the degree 2 slot, up to AN in a degree n slot, and define an addition of sequences and a multiplication of sequences. And the addition really wouldn't give us trouble, but the multiplication would be very strange and very awkward to define, and it'd be difficult to keep track of what's going on. By using polynomials, or the polynomial symbols with this indeterminate x, it helps us keep track of things. So the symbol x should really be seen of as primarily a bookkeeping tool, and it is definitely not a variable. So that's the first thing to mention. This is what we mean by indeterminate. It doesn't actually mean anything. The other thing that I want to mention is that you'll notice that our definition of degree here doesn't apply to the 0 polynomial. the zero polynomial is one in which all of the coefficients are 0. And so it can't be written as some sequence a0 plus a1x up through an x to the n with an not equal to 0. And this means that the zero polynomial has no degree. We do not define the degree of the zero polynomial, and you'll see that reflected in some of the theorems later, where we'll say things like, oh, this thing must have degree 0 or be the zero polynomial, things like this. It turns out that certain formulas for degree that we would want to use don't really work if we try to assign any sort of degree to the zero polynomial. The zero polynomial is special, just like the zero element of any ring is special, because when you multiply by anything, you just get 0 back. It annihilates anything it multiplies by. So we're going to go ahead and leave the zero polynomial as sort of special. We don't assign it any sort of degree. Okay. So in order to confirm that this set that we've described is in fact a ring with the operations that we've defined is very tedious. There are some ways that it can be made easier with clever and efficient use of notation, but proving that, say, multiplication of polynomials is associative is quite a pain. And we're not going to go through that here. If you really feel like you need to fill up 3 or 4 hours, then you might go ahead and see about confirming these things. We're going to forego it there. We're going to take it for granted that the polynomial ring R join X is in fact a ring, and it does inherit certain properties from its coefficient ring. And a lot of what we're going to be looking at today is what we can tell about the polynomials over a ring based on the properties of that ring itself. So the first thing that we'll notice is that every polynomial f belonging to some polynomial ring defines a function. Some function phi going from the ring to itself, given by phi of a equals f of a, where this symbol f of a means the expression obtained by replacing x with a in the polynomial f. This is called evaluating f at a, well, replacing all of its indeterminates, all of its with some ring element. So we can take, for instance, the following function, or the following polynomial, and build a function out of it. Let's let R be the ring Z mod 3Z, and let's let F be the polynomial 2 bar plus 1 bar x plus 2 bar x squared, which belongs to R of x. Of course, you can rewrite this in any order you like. Depending on what you're doing, it's common to write the terms in descending degree order. However, when working with proofs involving polynomials, it's often more intuitively clear to list them in increasing degree order. So we have that if we want to evaluate this function at 0 bar, this is the function 2 plus 1 bar times 0 bar plus 2 bar times 0 bar squared, which works out to be 2 bar. F of 1 bar is equal to 2 bar plus 1 bar times 1 bar plus 2 bar times 1 bar squared, which winds up giving us 2 bar again. And then F of 2 bar is equal to 2 bar times 2 bar squared plus 1 bar times 2 bar plus, I wrote this backwards from the way that I had it. Let me do this more accurately. Plus 1 bar times 2 bar plus 2 bar times 2 bar squared. So that's going to give us 2 plus 2 plus 8 is 12 bar, which is the same as 0 bar. So this is what we get. And it does turn out that the fact that we got a 0 out of one of these evaluations does tell us something about the function f itself. It's going to tell us that it can factor, but that is going to depend on the fact that this ring R that we started with is a field, and that statement won't hold in general. Okay, so the function phi that we describe here that goes from a ring to itself is very different than the polynomial f. So for another example, let's let g from R to R, g in the function r of x, with r being the same ring from before. Let's let g be the function x cubed minus x. Now, you'll notice that if we plug in any of the elements of R and evaluate this polynomial g at any of the 0 bar, 1 bar, or at 2 bar, we get 0 out of it. No matter what element we plug into G, we get 0 out of the evaluation process. That means that this function, so the function phi from R to R given by phi of A equals g of A is the 0 function. So that means that in particular it's the same as the function, it's the same as evaluating the 0 polynomial. So both the 0 polynomial and this polynomial g have the property that when you evaluate them at any element of the ring, you get 0 out of it. So they both define the 0 function from R to R, but they are two different polynomials. So, but g is not equal to 0 bar in R join x because they don't have the same coefficients. The coefficient of the polynomial 0 bar is 0 in every slot. All of the coefficients of this polynomial are 0, but some of the coefficients of g are non-zero. We've got a coefficient of -1 in degree 1 and a coefficient of 1 in degree 3. So we can have two different polynomials defining the same function. Now, this is something that's different from what we're familiar with. This is not something that can happen in polynomials over the real numbers or over the integers. This is something that that is special and depends on properties of the depends on the fact that we're working over something like z mod 3z. All right, so this is giving a little taste of what we're going to be moving forward on. As I mentioned, one of the things that we're going to be looking at is what we can say about the polynomial ring based on their coefficient ring. In particular, things like, can two different polynomials define the same function? So let's look at some of the properties that the polynomial ring inherits from its coefficient ring. So Theorem 112. If R is a commutative ring, then R has identity if and only if R join X has identity, and R is a domain if and only if R adjoin X is a domain. So the coefficient ring and the polynomial ring have to have the same properties in terms of having an identity or not and being a domain or not. We'll prove the result for the identity, then we'll leave the domain part as an exercise. We want to show that R has an identity if and only if R adjoin X has an identity. So let's suppose that R has identity 1. Now we can consider the constant polynomial 1 belonging to R join X. So this is a degree 0 polynomial whose 0th coefficient is 1 and whose all other coefficients are 0. So now for any f, which is given by a0 plus a1x plus blah 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 plus an x to the n, we have that 1 times f is equal to 1 times a0 plus a1x plus plus an x to the n. And then when we actually go to multiply these things out, you can go back to the definition of multiplication of polynomials if you need to, and we do need to for some complicated theorems. But most of the time, you can just use what you're used to doing as far as multiplying polynomials together. So in particular, if I've got some constant multiplied by a polynomial, then that works by multiplying by each one of the coefficients. So we get 1 times each one of the coefficients of the polynomial. Now in the ring F, in the ring R, sorry, element F, in the ring R, 1 is an identity, which means in particular that 1 times a0 is a0, 1 times a1 is a1, 1 times an is an, x to the n, and you'll notice that we've gotten back exactly f. So we have that 1 times f equals f. One thing that we haven't explicitly stated, but it is true that all, as we've defined them, all polynomial rings are commutative. The order of multiplication doesn't matter. And so in particular, since 1 times f equals f, then also f times 1 equals f. So in particular, 1, this constant polynomial 1 is a multiplicative identity. Now, what you will often find when working with these types of problems and trying to prove that a coefficient ring and the polynomial ring have the same behaviors, a lot of times what you'll find is that it's easier to prove things about the polynomial ring based on the coefficient ring than the other way around, as in this case. If R has identity, then R adjoin X has identity. This is a pretty easy argument. Going the other way is going to be a little bit more difficult just because we're starting with statements about R adjoin X, which is a more complicated ring than R. So we can say, let's suppose that R adjoin X has identity, and now we can't at this moment assume anything about the identity. We've just assumed that it has an identity element, and that element might look like any one of the polynomials inside R adjoin X. And so we have to assume that R adjoin X has some identity, and we can't assume anything about it. So we'll give it the a symbol G, and we'll say that it's polynomial b0 plus b1x, blah, 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 plus bn x to the n. And we want to somehow use this to show that the ring R has an identity. Now notice that for any element b in R, we'd love to use the additive, we'd love to use the multiplicative identity 1 right here in place of b, but we don't know yet that R has an identity. That's what we're trying to prove. So all we can say is that for any element b in R, there is a constant polynomial b in the ring R mod X, R adjoin X rather. And then since G is an identity for R adjoin X, we have that B is equal to G times B. And if we multiply these together, that gives us b0 times b plus b1 times bx plus etc. plus bn times b x to the n. But here's where we can compare coefficients. And in particular, to say that this polynomial on the left is equal to this polynomial on the right means that if I compare the coefficients in any degree, they must be equal. So comparing degree 0 terms, we have that the degree 0 term on the left equals the degree 0 term on the right. So in other words, we have b is equal to b0 times b. Now, since this holds for all b in R, this means that b0, whatever it is an identity for R. We've shown that there's some element of the ring that acts as a multiplicative identity, and therefore the ring R has identity. Now, once we have this, we could go back and conclude, okay, well then G had to be just B0. It had to be of only degree 0. However, we had no real way of knowing that ahead of time, or of concluding that. if we're just assuming that R join X has identity, we don't have the right to assume that that identity has to be degree 0. It turns out that that's the case, but we only know that once we go through and prove that this means that R has an identity, and therefore the identity of R join X is the constant polynomial of that identity R. All right, now, as I said, I'll leave the domain case of this theorem as an exercise. One thing that I do want to mention that we'll be using more or less tacitly throughout this discussion here is that the ring R can be seen as a subring of R adjoin X easily, where we identify by identifying elements of R with the corresponding constant polynomial. Thus, we can think of R as really being a subring of the polynomial ring R adjoin X, consisting of all of the constant polynomials, all the degree 0 polynomials plus the 0 polynomial. So we will sometimes, we'll often rather be switching back and forth between thinking of constant polynomials as elements of R and as elements of R adjoin X as we try to understand things about the polynomial ring in terms of the coefficient ring. Okay, so there's not a whole lot to be said about coefficient rings, about polynomial rings over arbitrary coefficient rings. As we see here, if the coefficient ring has some nice properties, is an identity, is a domain, then we get some nice properties of the polynomial ring. But to really get some powerful results out of a polynomial ring, we like for the coefficient ring to actually be a field. Polynomial rings over fields behave particularly nicely. And a lot of that comes down to results stemming from the following theorem. The following theorem is called the division algorithm for polynomials, and it tells us that you can sort of divide polynomials and get quotients and remainders just like you can for numbers. If you recall doing long division of polynomials in basic algebra for working with rational functions, this is the same sort of idea. So the division algorithm for polynomials states, let's let F be a field, now not just a ring, and let's let F and G be polynomials in the polynomial ring F adjoin X. Polynomial rings over a field are where we're looking at here, and in particular we want G to not be the 0 polynomial. Then there exist unique polynomials Q and R in the polynomial ring f of x with f equals q times g plus r, and with r equals 0 or the degree of R being less than the degree of G. We call Q the quotient and R the remainder of F with respect to G. So polynomials over a field can be essentially divided to get a quotient and a remainder in this way. We've seen this, we're familiar working with this over the real numbers or maybe even the rationals or the complex numbers, but this theorem shows that we can in fact do that for any field. Oh, this is also theorem 113. Now, notice that the absolutely key part of this is the condition on R. The thing that is going to make the division algorithm work well for us is that we're guaranteed that we can express F as a multiple of G plus R, where R is smaller than G in the sense of having a lower degree. In particular, this is going to allow us to do certain kinds of induction arguments where we could repeat this process over and over and over again, and each time the remainder R will either be 0 or its degree will drop. And so you know that eventually it's going to have to stop because the degrees are non-negative integers, and if you keep reducing a non-negative integer, eventually it's going to hit 0. We'll see some applications of this after we go through the proof. Let's see how this proof goes. So first note that if the degree of F is less than the degree of G, or if F itself is equal to 0, then we may take Q to be 0 and R to be just equal to F, which satisfies the existence of such a Q and R. I should have specified that we're going to handle the existence of such a Q and R first, and then prove that if these Q and R do exist, they have to be unique. So we're going to do existence first and then uniqueness, as is typical with problems like this. Because of this, if the degree of F is less than or equal to the degree of G, then we're done. We can find Q and R. So let us assume that the degree of F is greater than or equal to the degree of G. And we use induction on the degree of F. A lot of the results that we're going to prove about polynomials are going to use induction, and that's because we have this really nice number that we can associate to every polynomial, every non-zero polynomial, which is its degree. And the degrees are distinct or discrete. They only take integer values, and in particular only non-negative integer values, which means that induction is an excellent tool for dealing with polynomials. We will use induction on the degree of a polynomial often when looking at polynomials. So we use induction on the degree of F. The minimum degree of F that can be is 0. So if the degree of F is equal to 0, then we've assumed that the degree of G is less than or equal to the degree of F. So the degree of G also has to be equal to 0. And so F and G are non-zero constants in a field F. Here we're thinking about F as being a subring of the polynomial ring f adjoin x. And so f and g are non-zero constants in a field f. So in particular, this means that we can write f as f g inverse times g. And so that means that we're done where we take q to be equal to fg inverse, the constant polynomial fg inverse, and r to be equal to 0. So here's the first place where we are really using the fact that we're working in a field. In a field, every non-zero element has an inverse, and so we can construct this element f times g inverse in order to construct our division algorithm. And so this is the first place that you would fail if you wanted to try to prove this division algorithm for a polynomial ring not over a field. And we'll see that, in fact, the division algorithm completely fails if the coefficient ring is not a field. All right, so we've got the base of our induction. We've got the base case where the degree of f is equal to 0. And so now let's move on to the inductive step. So now suppose that degree of f is greater than or equal to 1, and for our inductive hypothesis, and for any polynomial, which, let's see, I'm looking ahead to get us, I want to use this consistent notation with what I'm going to use later. For any polynomial f tilde with the degree of f tilde less than the degree of f, there exist q tilde and r tilde in our polynomial ring, with f tilde equals q tilde g plus r tilde. And r tilde equals 0, or the degree of r tilde is less than the degree of g. So basically we're just stating, let's assume that the statement of the division algorithm holds for any polynomials of degree less than the degree of the polynomial that we're working with here. So this is technically known as strong induction sometimes, but it's completely equivalent to the induction where you just go up one step at a time. All right, so now we want to try to prove that we can get the same sort of results here, but without any of the tildes, with our degree, with our f that we have up here. So let's get some notation involved. Let's let f equal a0 plus a1x up through a mx to the m, and we'll let g be b0 plus b1x up through bn x to the n, where a, m, and bn are not equal to 0. We're guaranteed to be able to do this since the degree of f exists. It's not the 0 function, and by hypothesis, or the 0 polynomial, I should say, by hypothesis, g is not the 0 polynomial, and so in particular we can write them both this way, am and bn. In particular, this m here is the degree of f that we've assumed is greater than or equal to 1. So now let's let f tilde equal f minus am bn inverse x to the m minus n g. Now this is possible to do because we've first of all assumed that we're working in a field, and so any non-zero element like bn has a multiplicative inverse in the field. Furthermore, we've assumed that m, which is the degree of f, is greater than or equal to n, which is the degree of g, and so this m minus n makes sense. One thing you do have to be careful about with in rings in general, and polynomial rings in particular, is that the exponents that you write on an element have to be non-negative unless you happen to know that that element is a unit and has an inverse. So we let this happen. Now let's look at the leading term of this second piece of the puzzle, the am b to n inverse x to the m minus n g. It turns out that because we're working over a domain, the leading term of a product of polynomials is equal to the product of the leading terms. And so the leading term of this polynomial here is going to be a to the m, b to the m minus 1, x to the m minus n times the leading term of g is bn x to the n. Now when you have two single terms multiplying together, we just multiply the coefficients. am times bn inverse times bn is just am. Then x to the m minus n times x to the n gives x to the m. And notice that this is the leading term of f. So, since we're taking the difference of two polynomials that have the same degree and have the same leading term, the degree of that difference must drop. So that means that the degree of f tilde must be less than m, which is the degree of f, because we subtract these two polynomials. So now, by hypothesis, by the inductive hypothesis, f tilde is equal to q tilde g plus r tilde for some q tilde r tilde in f adjoin x with r tilde equals 0, or the degree of r tilde being less than the degree of f, being less than the degree of g. Sorry. So now let's take this equation defining f tilde and rearrange it for f. That means that f is equal to f tilde plus am bn inverse x to the m minus n times g. Now f tilde is q tilde g plus r tilde plus am bn inverse x to the m minus n g. And combining these together, we see that we get q tilde plus am bn inverse x to the m minus n g, x to the m minus n times g plus r tilde. And in particular, you'll notice that we've got some polynomial times g plus some polynomial r over here, where r tilde has precisely the conditions that we want. So we're going to let this be our q and this be our r. I'm just noting this before I go to the next page because I'm out of room. But letting this be our q and this be our r shows that it's possible to write f in the quotient remainder form that we've been looking for. So setting q equal to q tilde plus am b to the n inverse x to the m minus n and r equal to r tilde, we have that f is equal to qg plus r with r equals 0, or the degree of r is less than the degree of g. Okay, so this handles existence. Once we note that by induction, this holds for all polynomials f. By induction on the degree, we showed that if the statement held for all degrees below a certain number, then it has to hold for that number. And so by induction, it has to hold for every number, every degree. All right, so this shows existence. It remains to show uniqueness, but in this case, uniqueness isn't so bad. So now, suppose, or to prove uniqueness, let's suppose that f is equal to qg plus r, and is also equal to q prime g plus r prime, where r equals 0, or the degree of r is less than the degree of g, and r prime equals 0, or the degree of r prime is less than the degree of g. Let's rearrange getting all the q's on one side, all the r's on the other. Rearranging, that we have that q minus q prime times g is equal to r prime minus r as polynomials. Now, if q minus q prime is not equal to 0, then the left-hand side has degree at least the degree of g. If q minus q prime is not equal to 0, then q minus q prime is some polynomial, some non-zero polynomial, and in particular, the product of any two non-zero polynomials in a polynomial ring over a domain, such as a field, can only have a degree that rises. And so this product can have a degree that only goes up or stays the same. So in particular, the degree of the left-hand side has degree at least the degree of g. However, the degree of r prime minus r is at most the maximum of the degrees of r and r prime. And we know that both r and r prime have degrees which are less than the degree of g. So what we have is that if q minus q prime is not equal to 0, then the left-hand side of this equation has degree at least the degree of g, and the right-hand side, no matter what, has degree at most the degree of g minus 1, which is a contradiction. This is a contradiction. So we have q equals q prime, which shows the uniqueness of the quotient q. But furthermore, if q minus q prime is equal to 0, then the whole left-hand side is equal to 0, which means that 0 is equal to r prime minus r, and hence r equals r prime. So it's not possible to have two distinct quotients and pairs of quotients and remainders for a given f and g. So that means that the q and r are unique. All right, so big theorem takes a while to prove, but also very, very powerful. We're going to be able to use it to prove that functions, the functions defined by polynomials have zeros that correspond with the roots of polynomials, which in turn correspond to factors of polynomials. So it's all gonna play together, and the division algorithm is really key to this process. So let's see how that goes. We need a couple of terms. So definition 114. Let's let R be a commutative ring. Let's let F and G be in the ring R adjoin X. We say that F divides G, and we write F divides G with a long vertical bar like this. If there exists an H in the polynomial ring R adjoin X such that G is equal to FH. In this case, we say that F, the polynomial F, is a factor of G. And then finally, if A is an element of the ring and F evaluated at A is equal to 0, remember this is all happening in the ring, then we say that A is a 0 or a root of F. Technically speaking, we should really only talk about roots of polynomials and zeros of functions. But because of the way that we're defining roots of polynomials in this case, we'll often use the two terms basically interchangeably. Especially when working over a field, because the division algorithm gives us corollary 115, which relates roots and factors together. If F is a field, F belongs to the polynomial ring over the field F, and A is a field element, then the evaluation of F at A is the remainder of F with respect to the polynomial x minus A. So here, again, we are thinking of the field as sitting inside the polynomial ring. So F of A is by definition an element of the field. It's what you get when you take the polynomial F, replace all the indeterminates by this field element A, and you get an algebraic expression, sums and powers and multiplication. You evaluate all that, and you get some field element. But that field element is also a constant polynomial when we think of the field F sitting inside the polynomial ring F adjoin X. And so this is saying it's also the remainder of F with respect to X minus A. Now, when we apply the division algorithm to a polynomial and a polynomial F and another polynomial of degree 1, then the remainder is always either the 0 polynomial or of degree 0. In particular, this means it's always a constant polynomial, which is why it makes sense to talk about this corollary. Now, the division algorithm makes this quite easy. So by the division algorithm, there exist Q and R, polynomials Q and R in the polynomial ring such that f is equal to Q times x minus a plus r. So we have that these two polynomials on the left and right-hand side of the function are equal. In particular, we'll get the same result when we evaluate them both at some number. So evaluating both sides at a, we get that f evaluated at a is equal to q evaluated at a, some polynomial, times a minus a, because evaluating means replacing all the x's with a's, plus r of a. But remember that r is just a constant polynomial, and so evaluating a constant polynomial just gives you that polynomial back, essentially. Furthermore, we've got an a minus a term over here, which becomes 0, and so, in fact, we get back just r. This proves corollary 115 that if you want to evaluate a function at a particular element, that's equivalent to finding the remainder of the division algorithm applied to that function f and the degree 1 polynomial x minus a. This leads us to another result that we're familiar with from basic algebra over the real numbers, but it turns out to be true over any field, which is corollary 116. If f is a field and little f belongs to the polynomial ring over that field, then a is a root of f if and only if x minus a is a factor of f. So this is the corollary which relates factors and roots together in the abstract polynomial ring setting. The proof is an immediate application of the previous corollary. So we have that a is a root of f if and only if, by definition, f of a is equal to 0, which happens by corollary 115. This happens if and only if the remainder of f with respect to x minus a is 0. And again, just applying the definition of what a remainder means, this happens if and only if f is equal to q times x minus a for some q in the polynomial ring. And this is just by reading the definitions. This happens if and only if x minus a is a factor of f. So this corollary is very important for understanding the structure of polynomials, finding factors, things like this, and it's a very quick consequence of the division algorithm. This corollary leads us to one of the most useful and famous or well-known theorems in algebra from high school, from college algebra, which counts the possible number of zeros of a function. Now, to make this work properly, we need to give the definition of multiplicity. Definition 117. Let's let f be a field. Let little f be a polynomial in f adjoin x. And in this case, then little f, I jumped ahead a second, and little a root of f. The multiplicity of f at a is the largest number n such that x minus a raised to the n divides f. Now, because a is a root of f, we know that by the previous corollary that the factor x minus a must divide f at least once. It might do so more often than that, though, and so we can look at the multiplicity, which is the largest number that does it. We can use this to count the zeros of a polynomial function well. So Theorem 118, if f is a field and f is a non-zero polynomial in f adjoin x, then f has at most the degree f roots, counting multiplicity. Meaning that if a root has multiplicity 3, we count it 3 times, and so forth. Notice that this theorem doesn't make any sense if we try to include 0 here. 0 doesn't have a degree. Furthermore, for the zero polynomial, every field element is a root, so once again, 0 is sort of special here. So in this proof, we again proceed by induction on the degree of f. Now, if the degree of f is equal to 0, then that means that f is a non-zero constant polynomial, and so has no roots. When you take a constant polynomial and evaluate it, you always get that constant number back, and by assumption, f is not 0, and so when you evaluate it at any number, you get something non-zero, so it has no roots. So now, let's suppose that the degree of f is equal to n, which is greater than 0, and let's suppose that a is a root of f with multiplicity k. So now we may write that f is equal to x minus a raised to the k times g, where g belongs to the polynomial ring f adjoin x, and the polynomial x minus a does not divide g. So now, if b is any other root of f, then we have that 0 is equal to f evaluated at b, which is equal to b minus a raised to the kth power times g evaluated at b. Because b is supposed to be something other than a, b minus a is non-zero. Because f is a field, it's a domain, and so b minus a to the k is not 0. And so because of all of that, we have that g of b is equal to 0. So b is a root of g. So the point is that all of the roots of f either come from x minus a to the k or from g. And the a root appears k times, or with multiplicity k, and any other root appears in g some number of times. Furthermore, since we have this relationship f is equal to x minus a to the k times g, we have that the degree of g is equal to n, which is the degree of f, minus k, which is the degree of x minus a to the kth power. The degree of both sides of this equation have to be n, but the x minus a to the kth takes up k of those degrees, and so g has to have the remainder, n minus k. Now, by induction, n minus k is less than n. K is some number greater than or equal to 1. So by induction, this means that g has at most n minus k roots, counting multiplicity. So the roots of f come from exactly two places. They come from x minus a to the k or from g. X minus a to the k has k roots counting multiplicity, and g has at most n minus k roots. I should say has at most k plus n minus k roots counting multiplicity. Which is, of course, n, which is the degree of f. That finishes it up. That shows that f has at most number of roots equal to its degree. Now, one of the hypotheses of this result was that we were working over a field. Now, the same thing happens to be true when you're working in a polynomial ring over some set that's contained in a field. So the same result holds in z adjoint x, polynomial rings over the integers, and this is essentially, since z is a subring of a field Q, and so in particular that means that z adjoint x is a subring of Q adjoint x. So if I look at any polynomial in the ring z adjoint x, I can think of that as a ring inside Q adjoint x. Q is a field, and so I know that polynomial has at most n roots in Q, and so it has at most n roots in z. In fact, it probably has fewer because it might have some roots in Q that aren't in z that wouldn't come back. And in particular, this same result will hold in polynomial rings over any ring that is contained in a field. However, not every ring is contained in a field. So, as a remark, this result fails when the ring R is not contained in a field. So, for example, if we let R be Z mod 9Z, it turns out that Z mod 9Z is not contained in any field. Let's let F be in R join X be given by F equals X squared. Now, notice that F of 0 bar equals 0 bar squared, which is 0 bar. F of 3 bar equals 3 bar squared, which is 9 bar, which is 0 bar. And F of 6 bar equals 6 bar squared, which is 36 bar, which is, again, 0 bar. So F has at least 3 roots, even though its degree is only 2. And one can come up with lots of examples like this. If one works hard at it, you can come up with nearly any combination of you want F to have some degree and some much, much, much larger number of roots. You can do that by taking rings like Z mod 9Z. It turns out that the requirement that you need in order for the result above to apply, and perhaps we should have written it that way, is that you need the base ring to be an integral domain, or a domain as we call it. All right, so in the next lecture, we're going to talk about a type of ring called a principal ideal domain. Polynomial rings are over a field happen to be this kind of ring, and they have some properties that make them good to work with and are going to be very important as we move on to talk about things like factorization in abstract rings.